Kazra, we're going to do in chapter 7. We'll do actually. We're going to get to chapter 7 today. I think we'll get to chapter 7 today, or yeah, probably today. Tomorrow we're having the exam, so we'll do mostly chapter 6 today and a little bit of chapter 7. And so when we get to chapter 7, we're going to have to calculate the average atomic mass. And so we'll do a problem at that time. We'll do 2 of them. And so I'll explain it a little bit later. Okay. Yeah, no problem. Are there any other questions? Is 7 going to be included? No, 7 will not be included on the exam. Probably not all of 6 will be on there, although it's take home, so maybe I'll put some, definitely you'll have some nomenclature questions on the exam. Now, this being the exam itself is going to be a take home. And so this being a take home exam, there's a risk there that you aren't going to memorize the nomenclature. You have to have the nomenclature memorized, especially for Chem 1A, and you'll be at a severe disadvantage if you don't start memorizing it now. When you get to Chem 1A, it's just going to get harder and harder. There is no review, Natasha. The review is you're supposed to be reviewing your notes every day. That's going to serve as your review. And if there's something that's unclear in your notes, then you want to get it cleared up, for the test. And so that's why now, like right now, is a good time. If you didn't understand something that we presented in class, then you should ask about it. If there's a specific topic or subject, yeah, we can review that, no problem. Like how to calculate the average atomic mass or whatnot. But go back through your notes and see what questions you have from that, and then we can cover that tomorrow as well. For the polyatomic 8s, the periodic table is carbonate. Yeah, carbonate is 2-, not 4-. Because in class we said, no, that was the pattern. There's a different kind of pattern. The pattern is for the first, what we call the outer block versus the inner block. The outer block has a different pattern than the inner block. There are 2 patterns that we have to factor in. It's for silicon. Silicon's in the inner block, carbon's in the outer block, so it follows a different pattern. You would be right, it would be 4- for carbonate if it followed the single pattern of the inner block elements. So it's different. We're going to cover it again today. Okay, were there any other questions? All right, well, one thing I want to say is when people were uploading, let's say quiz 3, which is the swimming pool problem, a lot of people just took pictures of it, and putting pictures into a multi-page document is a little bit difficult. And so if there's, let's say the exam is going to be multi-page, probably like 2 pages long or something. And so we don't want to take pictures of each individual page and then upload them. And then pictures sometimes are difficult to open depending on what format they are. And so PDFs are always easy to open. So if you could, can you make sure that you don't just snap a picture and then try to upload that? Try to convert your document into a PDF, especially if it's a multi-page document. You can upload multi-pages and configure those for a single PDF. That is, just to combine those pages into one single PDF. And so can you take a look at this? This is what's recommended by El Camino. This is the Genius Scan app. And you can do this on your phone. That way you can, let's say if you have a 5-page document that you need to upload, you can just upload that as a single document rather than 5 separate pictures. Plus, if I need to print it out, printing it out, if you upload a photo, it uses up a lot of ink. So PDF use a lot less ink. Also, photos take up a lot of memory, and PDFs don't take up that much memory. So try to do this, especially if fall semester goes online, then Chem 1A you're going to have multi-page documents you'll need to upload. And so they'll require you to do PDFs. Let me know if you have any problems with that. Okay. All right, what I want to do at the start is to talk about the swimming pool problem. And so let's take a look at the, I'll omit the names here, but these are, I got 4 submissions here. And so let's take a look at all 4. This one is great. This one, because it's great because everything's labeled appropriately. So here, you know, we have 18,000 gallons of swimming pool water. This one need not be labeled because this is unrestricted. We can use this for anything. Certain things are restricted. We can only use them for specific applications, but this one is unrestricted. So this one you don't have to label. You know, 1 gallon of anything, you know, is 3.785. Now, you don't have to, you know, some numbers we want to memorize, and this is one of those we'd like to memorize. And so, you know, it's a common one, and therefore it's worth memorizing, and that is this. If you're good at memorizing, then maybe memorize it to 5 sig figs like this, but in exactly 1 gallon, I just memorize it to 4 sig figs. That's 3.785 liters. And so it makes it a little bit easier to memorize. Like that. 3.785. So I would have used this here. This is, you know, not exact. We could get it exact in our book, it's exact, but it's too many digits. Okay, so this is, but regardless, it's fine. If you want to label this is swimming pool water, this is swimming pool water. Okay, but it could be 1 gallon of milk is 3.7854 liters of milk, it's whatever. All right, 1 liter is 1,000 milliliters. This one is also unrestricted. This one's valid for everything. And so this one, you need not label it. So you can save a little bit of time. You don't need to label this one. You don't need to label this one because the units would just carry through. Gallons would cancel, swimming pool water carries through. Then liters cancel, swimming pool water carries through. Now this one is restricted. This one is only valid for swimming pool water. And so we did, looks like you guys did gallons, converted it to liters of swimming pool water, to milliliters of swimming pool water, to grams of swimming pool water. And when we look at this one, it looks as if the swimming pool water has close to the same density as pure water, you know. In fact, this is looking pretty, and so the amount of chlorine in here and the amount of other substances is pretty low. If we carried out the density to maybe 6 sig figs, then it would be different. You know, it should be a little higher because there's stuff dissolved in the water. You know, you wouldn't want to drink it. You wouldn't want to base the purity just on density alone because it doesn't change that much from pure water since it's fairly dilute. Well, anyway, the swimming pool water, we convert milliliters to grams of swimming pool water. That's good. Okay, now this one is restricted as well. This one is for grams of swimming pool water. This one has to be labeled. We want 1 gram of pure chlorine for every 1,000,000 grams of swimming pool water. So we can figure out how many grams of chlorine we have. Then once we know how many grams of pure chlorine we have, we're going to get that from the chlorinating solution. And so we know in the chlorinating solution, it's not pure. Out of 100 grams of chlorinating solution, there are only 7 grams of pure chlorine. So that cancels out nicely. That gives us grams of chlorinating solution. And then this one's restricted also. You know, this one's not for everything. So this is 1.10 grams of pure, not actually, I shouldn't say pure, a solution's a mixture. So 1.10 grams of this chlorinating solution mixture is equivalent to a milliliter. Now this density is a bit higher than pure water, you know, because there's a lot of chlorine dissolved in there. You know, pure water is around 1, right? And that gives us milliliters of chlorine solution. And then here's a milliliter to liter conversion. Here, you know, I don't like to memorize 2 different ones. You know, well, if it's easy for you, go ahead. But I'd like to keep it the same. So I would have done 1 liter on top and 1,000 milliliters on the bottom to keep it the same. And that way I always write write it the same way rather than writing different variations of the same conversion, since these two conversions are the same. Here, just flipped, upside down. And so 1,000 milliliters per one liter is 1,000 milliliters, and that gives us liters of chlorinating solution. And so you get a lot of digits here. We aren't allowed that many digits. This one was a bit ambiguous. I talked about the sig figs here, as being 1 sig fig. If it's 1 sig fig, then it's 1 liter. We just say add about a liter, but a liter would be overshooting it. And so it would be nice to have more sig figs. So if it's ever uncertain, having more sig figs is better than having too few sig figs, about that. But this is correct. That's the right answer here. 0.885 if we did it to 3 sig figs. Well, sometimes we do in these problems is we just assume a hypothetical problem in which we're doing exactly 18,000 gallons. This would limit it to 2 sig figs, but if we say, hypothetically, if we had exactly 18,000 gallons, approximately how many liters? Let's say the manufacturer made this, to 7% chlorine. If they made it to 7% chlorine, exactly, then this is how much we'd need to, we'd get it to 3 sig figs, because the densities, densities have 3 sig figs here. And densities aren't good beyond 3 sig figs, I think. Here. All right, so that's 885 milliliters. Yeah, this would be 885 milliliters. We multiply this by 1,000 to get milliliters, or move the decimal 3 over. So it'd be 885 milliliters, say that. Or we could use dimensional analysis. If we use dimensional analysis, we take this liters and convert it into milliliters. Now, this is valid for anything. A liter of anything is equivalent to 1,000 milliliters of that. So we don't have to label that here. This should be labeled, the chlorinating solution. Solution's abbreviated SOLN. So you don't have to write it all out, so you could just say chlorinating solution, use Cl for that. Now, chlorine, when they say 7 grams of pure chlorine, isn't chlorine a diatomic element? If it's 7% chlorine by mass in this chlorinating solution, then we say 7 grams of chlorine per 100 grams of solution. This would be the chlorinating solution that you buy at the swimming pool supply place, let's say. Now, what kind of chlorine are we talking about? Because when we're talking about chlorine, isn't chlorine the diatomic? It's not that happy being alone, so it likes to be diatomic. So is that 7 grams of Cl2? And the answer is not. This chlorinating solution doesn't contain Cl2. It contains like bleach, which is sodium hypochlorite. And in that, it has 7 grams. And, we're going to talk about this today, but usually the chlorinating solution consists of bleach like this. And then there's chlorine here. So it's not 7 grams of sodium hypochlorite, pure sodium hypochlorite. It's 7 grams of actually chlorine atoms contained within this. And so what they're looking at is they're just looking at the amount of chlorine atoms in grams. And so that's why it's not Cl2. Otherwise, the problem that you could use Cl2, it's just it would degas out of there. That is, it would be like hydrogen peroxide. If you use that stuff, eventually it'll go flat. And so here, and so this is what we have 7 grams of. We're going to have a lot more than 7 grams of this because there's sodium atoms and oxygen atoms, so we got to account for that weight too. But in this whole thing, we're going to have 7 grams of chlorine. And so this is why using Cl is okay. 7 grams of Cl, pure chlorine atoms in this 100 grams of chlorinating solution. Okay, let's look at some of the others here. So this is safe. Although it's a lot of work to have to label everything, it's safe. The problem is when people don't label things, then it's easy to make a mistake. And so what you want to do is you want to spend a little bit of extra time to label stuff like this. And that will make it a lot easier to do harder problems. When it comes to harder problems, the biggest failure is not labeling stuff. I mean, that's the #1 reason why people can't solve harder problems, is they don't take the time to label things, and they don't take the time to make sure the units cancel. Okay. Let's take a look at this one here. Okay, this is an alternative way of solving this. They did it, rather than stringing it all together in one step, you know, like this, they broke it down into multiple steps. And so here, let's take a look at this. So here they did this. Now, this one, you know, like I said, I don't like to do too many variations of this. I mean, if it's easy for you, go ahead and do that. And this is too many sig figs to memorize, you know. Even though it's more work, it seems to be more work, I think it's less work. It's less work if you just have a few that you memorize that you can string together. And so, you know, if I do this, I can go gallons to liters, no problem, and then liters to milliliters, no problem. But I don't like to combine these, you know, I don't like to combine them to save a step, because combining that actually means you have to do another mental step. And so it's much easier for me just to memorize, okay, 3.785 liters in a gallon. And then it's much easier for me to memorize 1,000 milliliters per liter, rather than coming up with another one that you have to memorize. The other one would be the combined one here. Well, I don't want to do that. I'd rather just do it in 2 steps, and it saves me time. And then the other thing is, it gives me a mental check. You know, if I use this enough, I see, oh, this is correct. And if I use this all the time, I see that this is correct too. This is, what did I do here? This is not correct. Here to here. I need one more arrow there, let's say. Well, anyway, so I don't like to combine things, but okay, here. Now, they have it labeled here, swimming pool water. So this would be milliliters of swimming pool water, that's fine here. Thus, the mass of water, M, is given by the relationship. Okay, I don't like to use algebra. If I can avoid using algebra, I'd like to just do it by conversion factor, as in the above problem there. Okay, but it's okay. I mean, to each their own preference, you know. The other thing is, you got to be careful about rounding. Don't round until the very end, you know. So just carry all the digits in your calculator if you're going to do this multi-step, and then just continue on there. Okay, let me clear these drawings here. Okay, so so now we have grams, but grams of what? And so let's say mass of water. And so we have to carry that down here. This has got to be swimming pool water. So grams of swimming pool water. You know, you have to, just so you make sure, you have to make sure, and 1.1 chlorine solution. Okay, so here, this is grams of swimming pool water. Next, volume of chlorine required. Level of chlorine is 1 ppm, i.e. 1 part of chlorine per million, or 10 to the 6 parts of water. So mass of chlorine present, 1 ppm. Okay, this one is, you know, I would prefer to do it, you know, because looking at this, automatically what I see mathematically is it doesn't work. Because if I take grams here and grams, I should get grams squared. Right, grams times grams gives you grams squared. And so I see a problem with dimensional analysis here, and that's gonna create problems. Even though this is the correct answer, this is going to create problems in the future. So you want to change this now. And the way you change this now is you got to make sure the dimensions work out. Yeah, this is kind of correct, you know, the multiplication, the numbers are correct, you know. So what we do is we do something like this. Instead, okay, 1 ppm is 1 part of chlorine. So we have 1 part of chlorine. Cl for a million parts of pool water. So this is pure chlorine per million parts of pool water. And so this is a part per million. A percent is a part per 100, you know. So if we had 7 parts of chlorine, pure chlorine, per 100 parts of chlorine solution, SOL, and again, it's abbreviation. Okay, but we have different percentages and we have different ppm. This is percentage by mass. Okay, this is ppm by mass. Now, if it's by mass, I could put any mass in here. I could say 7 pounds of pure chlorine per 100 pounds of solution. But the most convenient one for us is 7 grams. You know, 7 grams of pure chlorine per 100 grams of chlorine solution. That's going to be the. Now, the same thing goes here. You know, this is by mass also, by mass. I better try to spell this or spell it out, by mass. And so I could put one pound of pure chlorine per million pounds of pool water. That works, you know, as long as the 2 mass units are the same. But for us, the most convenient is grams. So I'm going to have 1 gram of chlorine per million grams of pool water. Now, if we use that here instead, the units are going to work out because we have to label this. If we don't label these, then it doesn't cancel out properly and we get funny units. You know, this should have been grams squared mathematically, you know. And so this is going to come out. And then you can tell, well, what is a gram squared? Well, there's no such thing as a gram squared. So you know you made an error there, you know, and so it gives you a quick check to see if you made some kind of error that can be corrected, you know, just by going back and making sure everything's properly labeled. 1 gram of chlorine pure per million grams. And so the 2 grams aren't the same. You're multiplying grams of pool water times grams of pure chlorine to get grams squared, and you didn't cancel out the grams down here, which is grams of pool water. And so this is very specific. This is restricted. You can't use this generically. So we can get the grams of pool water to cancel the grams of pool water, and that leaves us with grams of pure chlorine. This is grams of pure chlorine. So it's not grams squared, it's grams of pure chlorine. Well, you have that here because you have the level of chlorine. So I assume you're doing it right, but you got to set it up mathematically correct. Otherwise, it's kind of like magic, you know, going from here to here. You know, magically you get the grams of chlorine. I know the calculation's correct, but it's a bit of magic here mathematically. Okay, let's go on here. So now, okay, now this is good. It helps having these descriptions here, you know. And so we got the level of chlorine. This is grams of pure chlorine. Pure chlorine, we have to differentiate that from chlorine solution. Chlorine solution is a mixture. You know, chlorine is just how many grams of the chlorine atoms we need. And this is how many grams of mixture we need here. Okay, again, there's something funny. You know, the units are magically appearing here, but I don't necessarily see it here. Okay, so if we do 100, that cancels and 7 cancels. And then what is M? Well, okay, M is 68.1. And so we'll see what's going on here. And then are there no units here? You know, and then the units come out here. And so again, you know, this can be fixed. You know, the answer came out correct, but you have to be careful here, because if the units don't work out, then it's not going to come out correct. And I see that you like to set things up algebraically, but we're going to try to get away from algebraic and go to dimensional analysis. 68.1 grams of pure chlorine. Pure chlorine. Okay, then we know that for every 7 grams of pure chlorine, we're going to need 100 grams of this chlorine mixture. And so we'll call it the chlorine solution. Okay, so we don't need an algebraic. In fact, you know where a lot of these algebraic equations come from? A lot of these algebraic equations come from dimensional analysis. You know, let me tell you, I was taking an engineering class at UCLA, and the professor asked us to calculate something, but you know, in engineering, you need the equations. You're supposed to be given the equations. The professor didn't give us the equations. But I thought, oh, that's easy, because he gave us all these variables and constants, and I could just make an equation myself by just multiplying and dividing all these numbers to get the right dimension. So all I did was I just used dimensional analysis to derive the equation for what the professor was asking. I didn't need to be given the equation, and to my surprise, because I was the only chemist in that class, and the rest were all engineers. To my surprise, very few people got that question, and I thought it was such an easy question. It was such an easy question, and I asked the other students, "Why didn't you get that question?" They said, "Oh, we're never given the equation." And then I thought, you're never given the equation. You have to have the equation in order to solve that problem. And so that surprised me that they actually needed the equation to do a dimensional analysis. And so, you know, if I'm not given the equation, like there are many equations, like density is mass over volume. If I didn't know that, it doesn't matter to me, you know, or proportionalities or whatever else, because I just do it based on the units. You know, I know I'm doing it with the wrong equation if the units don't work out. Let's say I get grams squared of pure chlorine, then I know I got this upside down. You know, I shouldn't be multiplying, I should be dividing by it, you know. And so here we don't need an equation for this. We just got to make sure that the units cancel out. Grams of pure chlorine cancel out, and that gives me grams of a chlorinating solution. And so it's going to be 100 divided by 7, which is, this is correct, right? Here. But the units, you got to make sure the units don't work out, because this is grams of, originally this is grams of pure chlorine. There are no units here. These are dimensionless. That's not right. This should still be grams of pure chlorine, according to the algebra here. And so, so you got to show more, even though, yeah, this is great. You're explaining what's happening here, so I can see what's happening, but you're working magic again with the dimensions, and you can only go so far with that. You know, when things get hard, you can only go so far. So what you want to do is you want to build good habits now. If you build good habits now, then they'll make more advanced problems so much easier, you know. All right, so again, here I wouldn't use an algebraic equation, I just use dimensional analysis. But anyway, so you're converting from grams of chlorine solution to milliliters of chlorine solution using the density here. And so here they would cancel out, because this is grams of chlorine solution and this is 1.10 grams of chlorine solution per milliliter of chlorine solution. So we get 885 milliliters of chlorine solution, which is the correct answer. Okay, let's see. This go on to this one. So this one is similar in the sense that giving me a verbal explanation of what's going on. So in this step, it looks like convert gallons to milliliters. All right, so 18,000. Again, I would have the units here, gallons, and then I wouldn't memorize this to 5 sig figs. I just memorize it to 4 sig figs, 3.785, or use it. You know, you don't. It's not like you have to memorize. You use it over and over, and when you use it over and over, you always want to use it the same way. That way it's easier to memorize, and repetition helps you memorize things. So you go 3.785 liters per gallon, and you use it over and over again. If you have too many variations, then they get mixed up. You know, you try to keep the number of variations to a minimum and then use those repeatedly, even if it means stringing together more steps. Anyway, this is gallons. This should be gallons. The important thing about dimensional analysis is not just numbers. you know, it's dimensions too. And so you got to show me the dimensions as well. So be careful of that. Here, this should be gallons, this should be liters per gallon because this liters of pool water. And then this is times 1,000. Okay, this is 1,000 milliliters per liter. Liters cancel, that gives us milliliters. All right, so we're at milliliters of pool water here. Okay, then, okay, that's step one here. Step two, find the mass of chlorine. So again, mass of chlorine. Okay, this one is not so clear as to the thinking here, you know. And so a little bit more explanation would help, but it's actually correct because, you know, this is the milliliters and this is the grams, except there's a step missing. Now the step that's missing is this. This part per million is based on mass, but this is volume. And so the step that's missing here is how did you go from volume to mass, you know? And so here, it worked in this case because the density is 1. However, if the density is not 1, it wouldn't have worked unless you did it and you just didn't show me, you know, you guys didn't show me here. Because as you recall, the ppm level for the pool, it's 1 ppm, so it's 1 gram of pure chlorine per million grams of pool water. So here you're going from milliliters of pool water. And so how did you get from milliliters of pool water to grams of pool water? You know, because that's what we're using here. And so you didn't show me that step. Maybe you did it, maybe you didn't. If you didn't do it, you're going to be in trouble because you got lucky. You got lucky because the density of pool water is, you know, for every 1 milliliter of pool water, there's 1.00 grams of pool water. So it's the same thing, you know, 1 milliliter is 1 gram. However, if let's say the density weren't, let's say the density is 1.5, then if you didn't account for that, then this is wrong, you know. Okay. All right, so anyway, what I would have done was done another step, convert milliliters of pool water to grams of pool water, all right? Then once we get the grams of pool water, then we figure out the grams of chlorine using this here. Okay, then we could get that here. And then find the volume of the solution, the chlorinating solution. So, well, this is the grams of chlorine. This works, but, you know, it's hard to say, you know, looking at this, what's going on here, you know, when you just have the numbers. And so dimensional analysis, we have to look at the dimensions of the units. A lot of people, you have to watch out because if you don't write the units, when I was taking Chem 4 equivalent, if I didn't write the units, like gallons here, right here, then I lost like half, minus 50% credit, because each of these, half of it's the number, the quantity, the other half is the unit. So every time I was missing a unit, I lost 50% of the grade. This one, there's another 50%, you know, of the grade for that particular step, you know, whatever. A lot of instructors are still like that. Some instructors will take off more. Some instructors might not take off anything, but dimensional analysis, you know, it's not just a number. The problem is, you heard about the huge failure. There was a joint effort between Europe and the US. This was a space mission. I forgot which space mission it was. This is almost unbelievable. I mean, it's hard to believe if it didn't actually happen, but it actually happened, which is unbelievable. In the US, they were using inches and feet. you know, standard English units. In Europe, of course, they're using the metric. And engineers have a problem with writing units. Engineers like to just write numbers. I know this because I've taken a number of engineering classes. They just like to write the numbers. So 0.53 and 513. Okay, oh, in Europe, they're going to use 0.513. But the problem is in the US, they're automatically assuming this is 0.513, let's say inches. In Europe, they're thinking, oh, this is 0.513 centimeters or something. I don't know. So some kind of mismatch happened there, and they lost, I think, $40 million worth of equipment because mission was a failure. I didn't read all the details, but it's one of those things that are almost unbelievable. But it's easy to see because, you know, for some reason, people don't like to write units. But start getting in the habit now. I mean, it's early, so you just develop that habit. And you might think, it takes too much time. No, it doesn't take too much time. Making a mistake takes much more time. Arguing with a professor for extra credit or whatever, this or that, or credit for this or that, you know, that's much more time consuming. And so try to get that. Okay, here are units. So this is good, except this is okay for Chem 4 level questions. Anything harder than Chem 4, you're in trouble. Let's see why you would be in trouble here for anything harder than Chem 4. Okay, so let's keep track. This is gallons of pool water. Okay, this one's fine for anything. This one's fine for anything, right? So we're left with milliliters of pool water. So at this point, we have milliliters of pool water. This one is only valid for pool water. So for every 1 milliliter of pool water, we have 1.00 grams of pool water. So this one is fine. Now we have grams of pool water up to this point. So grams of pool water, things are flowing, good. Okay, now we have a serious problem because here, of course, grams is going to cancel out grams, you know, here. But this is not grams of pool water. Do you see what is this? This is grams of pure chlorine. And so that's not going to cancel this. And then up here, I have grams of chlorine solution. So I'm going to have very weird units. You know, when I add this one, I have grams of chlorine solution times grams of pool water divided by grams of pure chlorine. So I have a very strange unit going on here. Okay, then let's take a look at this next one. This one is restricted. This one's only valid for the chlorine solution. So this is 1 milliliter of chlorine solution for 1.10 grams of chlorine solution. So for every milliliter of chlorine solution, it weighs 1.10 grams. Okay, now the grams of chlorine solution I see cancel. So grams of chlorine solution will cancel this. But I still have this weird unit here, grams of pool water over grams of pure chlorine. Okay, then I have this one. So I got milliliters of chlorine. Okay. Then I have milliliters of in here added into the mix. Milliliters. Okay, so so it ends up that there turns out to be a problem here. That's happening here. And so let me just punch out the numbers here and then see what I get when I punch out the numbers. The units are going to be kind of really weird here. And I'm going to get 18,000, okay, times 3.785 times 1,000, okay, times 100, oops, divided by 7, divided by 1.1, divided by 1,000. I don't get your number here. When I do this calculation using this, I get this. I get 884,805 liters. So this, redo the numbers here. Let me just double check the calculation again. 18,000 times 3.785 times 1,000, although I could cancel that if I wanted, times 100 divided by 7 divided by 1.1 divided by 1,000. Yeah, 884,805 liters. But the problem is it's liters times grams of pool divided by grams of chlorine pure. And so one thing, this doesn't make sense. And another thing is the number is way off. And so we could have avoided this. Okay. Yeah, you forgot to, yeah, okay, that's fine. If you forgot to put some conversions in there, then that would work. But one way to tell if you forgot, because do you see how it's all canceled there? This got canceled, that got canceled, that got canceled. You know how things get canceled? Things get canceled because, you know, of this. Normally it would work in Chem 4 problems, but here it doesn't work because these grams are different things. You know, the grams of pool water is not the same as grams of chlorine, which is not the same as grams of chlorinating solution. And therefore, here, this is good. This is labeled properly, but the others have to be labeled in order to make sure it cancels out. So that's fine. Anyway, I'm not going to take off anything for this, so don't worry about it. But in the future, you know, it's potentially, you could lose points potentially if you do this. You know, make sure things work out properly. All right. All right, the same thing with the other one. We're going to continue the other quiz at the end, you know, with that blood alcohol one. And for the blood alcohol one, that's another one that's important that you keep track of all the units. Now, there is one other thing I want to say about this problem. And one other thing I want to say is we had to make an assumption for this. Okay. And so let me talk about that now. There's something wrong with the math here. I don't know if anybody noticed it, but did anybody notice that there is something not being factored in? Oh, let me tell you what it is. We had to make an assumption. Let me write down what the assumption is. Okay, assuming that the volume of the pool, does not change significantly with the addition of the chlorinating solution. All right, why did we have to make this assumption to solve it like this? The reason we had to do that is, let's say we came up with a calculation. Okay, let's say we had very cheap chlorinating solution. Let's say our chlorinating solution was very dilute. Very dilute. Dilute meaning it wasn't very concentrated. Rather than 7% we call that concentration or the composition, rather than having 7%, let's say it had something like 7 parts per million chlorine. Well, that means we'd have to dump in lots. If it was 7 parts per million rather than parts per 100, then a part per 100 is 10 squared, a part per million is 10 to the 6th. So the difference between that is 10 to the 4th. And so we'd have to add 10,000 times more. And so rather than adding like eight, let's say if it were 7, if the chlorinating solution were 7 ppm, rather than adding 0.885 liters, we'd have to add 10,000 times more, or 10 to the 4th. So it would be 8,850 liters. So like 7 ppm. Then 8,850 liters of chlorinating solution required. Well, 8,850 liters, how many gallons is that? So 8,850 divided by 3.785 liters per gallon is 2,380. This is not, of course, this is not, nobody's going to sell chlorinating solution that dilute, but I'm just giving you a hypothetical example here. Oh, shoot. I didn't want to clear that. Let me undo that here. And let me erase this here. 2,338 gallons. If you have to add 2,338 gallons, this is a problem. This is a problem. Okay, the problem is we calculated the chlorine level. Remember, the chlorine is 1 gram of pure chlorine per million grams of pool water. So we calculated the amount of chlorine we need based on 18,000 gallons. But what happens is if we add 2,000 more gallons to that, then the swimming pool is not going to be 18,000 gallons anymore. The swimming pool is going to be 20,000 gallons. So if you have 20,000 gallons, you're going to need more chlorine. And so we aren't adding enough chlorine. In fact, we're going to have the same problem, because if we add a liter, this liter is not going to have the required chlorine level. You know, so if we add about another liter here, it's going to be 18,000 gallons plus 1 liter. And we didn't compensate for that plus 1 liter or quarter gallon. So this is going to be 18,000 and about a quarter gallon. But we calculated the chlorine level based on only 18,000 gallons, not this plus liter here. So this plus liter that we're adding, and it's going to change the volume of the pool, is not compensated for. Does this make sense? If this doesn't make sense, don't worry about it too much, because this is going to be a Chem 1A style. This is a Chem 1A style problem already, but this would be Chem 1A level kind of thing. Okay, so what we're going to do is we're going to assume, well, if we add less than a liter to an 18,000 gallons, does it change the volume much? Yeah, it changes the volume a little bit, but not much, you know. And so what we can say is that this is a negligible addition. So what we're going to say is, so what we say is that this is a negligible addition. Therefore, 18,000 gallons, plus about 1/4 gallon, plus about 1/4 gallon. So 18,000 plus 1/4 gallon is about 18,000 gallons. That's what we're saying here. So it's barely, it doesn't really change much. And so this is going to be close enough, you know, close enough. Okay. But what if you didn't want close enough? You know, even, okay, I can understand if we're adding a huge amount of chlorinating solution, that's going to change the pool volume significantly. And therefore, we're going to have to compensate for that. And what's the math involved there? But let's say, you know, I don't want this close enough. I want to know what the number is. So even if I add this little bit here, I want to be able to compensate for it by adding, you know, I better add a little bit more chlorinating solution. How would I do that? You know, how would I do that? Now, this is going to be advanced. So you could ignore this if you're just, you know, if this is, if you do not want to make an assumption, if you do not want to make this assumption, then we have to do a, you know, two unknown equation type. In other words, we have to do a series of equations. All right, one equation is the total volume of the pool after we add the chlorine solution. And so total volume of the pool. I'm going to use V for volume of the pool. The total volume of the pool is going to be our original 18,000 gallons plus the gallons of chlorinating solution. And so we're going to have to convert it from liters to gallons. Gallons of chlorinating solution. And that's going to give us the total volume of the pool. And so this total volume of the pool, we plug in here. Okay. And so this is one equation here, the volume of the pool. And this is the second equation here. And so what we do is we'll just call this X here. Let me undo that. So we're going to call this X equals X. So what I'm going to plug in here, rather than plugging in 18,000 gallons, I'm going to plug in 18,000 gallons of pool water plus X gallons of chlorinating solution. And that's going to give me the total volume of the pool. And that way I can calculate the correct amount of chlorine required for that. And so it could be a little amount. If the chlorinating solution is concentrated, it'll be a small amount. The more concentrated this is, the better, because that's less we have to add. The more dilute that is, the bigger the problem is, because the volume is going to change more significantly for this. And so we have to solve for X in this particular case. And this is going to equal, well, what does this equal? So if that's my X, then what is X? We've got to figure that out, because we're solving for Y. Actually, no, we're solving for X. This is going to give us X here. X. Actually, we need one more conversion, sorry. If we add one more conversion to this, then we can figure it out. And the one more conversion here is we're going to go from liters to gallons. So 3.785 liters is equivalent to a gallon. And so liters will cancel liters. That leaves me with gallons of chlorinating solution. That's X. X. Gallons of chlorinating solution. So we have X, right, in one equation. And so we solve this algebraically for X. And so we get rid of all the units and then multiply out all the numbers and then solve for X here in this one equation. And then we have the correct amount. It's going to be a little bit higher than this. It's going to be a little bit higher than this because we have to add a little bit more chlorine, because the volume increased a little bit from the addition of the chlorinating solution. All right, again, this is advanced, but it's common to simplify things. You know, how many people want to do two equation to a known problem? Not that many, you know. And so assumptions are common because it's, when we make assumptions, it makes the math easier. Are common to make math easier. Okay, so we got this in terms of a single variable. The math isn't too terrible on this one, you know, we could figure it out. In fact, it'd be pretty quick. We could calculate this in a few minutes, but oftentimes we'll just not do that. And just assume that a liter isn't really going to impact 18,000 gallons much. Okay. And so the answer is going to be close enough. All right, any questions on this, the pool water problem, before we leave it? All right. Okay, let's move on then to the next problem. That's nomenclature. No. All right, we were talking about the eights last time. And so we're just going to continue with this, the eights now. And so from current slide. All right, so there are eights that you just plain have to memorize. And then there are eights that we can get off the periodic table. And so what were those? Let's just review those quickly. The eights that we just have to straight memorize. And I think the easiest way to memorize these is just write them. If you write them down like 50 or 100 times over and over, then they get into your motor memory. It's like, and once they're into your motor memory, it becomes automatic. You don't have to think about it. And so let's see what some of the eights that we need to memorize are. And so what are some of the eights? Well, there's acetate is a very common one, acetate. Yeah, permanganate's another one. What's the formula for acetate? The way, you know, I just write it over and over, C2H3O2 minus, or there's another one, CH3COO minus, which is the, this one you don't really have to, you'll see it sometimes, but 232, you should memorize it. So I do 2321. That's good. H3CO minus is the same as this. The only thing is sometimes we don't write the H first, because sometimes when we write the H first, we might mix it up with an acid. Acetate's not an acid, it's actually a base. But acetate's a good one. Permanganate, it's another one we just write over and over again. The way I memorized it is I don't use flashcards because then it doesn't get into your motor memory. I use, just write it over and over, MnO4 minus, MnO4 minus. That way when it comes to a test, you're asked permanganate, you just write it. It becomes ingrained. Permanganate, chromate, CrO4 2 minus, dichromate, C2O4 2 minus, oxalate. Oops, what am I doing? I was getting ahead of myself. C2O4 2 minus is oxalate. Dichromate is Cr2O7. CR2072-. Now di usually means two. So it sounds like we have two chromates. And in fact, we do have two chromates. But the way they link up is that it doesn't like to form an oxygen-oxygen bonds. Oxygen-oxygen bonds aren't that stable. So if we look at chromate, let's take a look at chromate. And then try to visualize two of the chromates coming together. Let's take a look at that here. I'll probably just go to Wikipedia. Okay, so we have chromate here. Chromate occurs as these type of units here. It'd be something like this. It's like a chromium stuck in the center, and then there are 4 oxygen atoms bonded. So it's CrO4, and then they show the charge, which is a 2-. We'll talk about the charges, how they come up with these things here. Now, when we have two chromates, they don't like to link two oxygens together. When you have an oxygen-oxygen bond, those are given a special name. An oxygen-oxygen single bond, that is, it has one line. These are called double bonds here. There's 2 lines here. You can see the double bond has 2 lines. A single bond has 1 line. So you can see that here. Oxygen-oxygen single bonds are unstable. And so let's take a look at dichromate. So when two chromates link up like this, we don't have this. We don't have, here's one chromate here, and then it should have 1 oxygen, and here's another chromate. It should have its own oxygen, so there should be 2 oxygens here linked up. But what they end up doing is they end up losing 1 oxygen and just share 1. And so this is a chromium-oxygen-chromium link here, or bond. And so this is dichromate. That often happens in this kind of stuff, is we lose one of the oxygens here. And so it's CR2, rather than O8, it's going to be O7 because one of the oxygens has been lost. Where did it go? Well, it went somewhere else. We'll talk about that. It doesn't disappear, but it went somewhere else. So here you can see this is potassium dichromate here, which is very common. All right, let's take a look at some other stuff here. So dichromate, CR2O7, not CR2O8, 2-. And what else? Was there any other one that I'm missing? There are more, you know, cyanate, but I'm not going to make you memorize cyanate. It's not that common. It should be CNO-. These are the common ones that you'll encounter here. And so these you want to memorize. And so work on memorizing these. Others you don't have to memorize. Others we get it from the periodic table. And so this is the pattern off the periodic table. There's the outer and the inner block. The outer starts with boron. Boron's in group 13 or 3. This is 3A. Or 3A. And so it's in group 13 or 3A. And so when we look at borate, this is our anchor. We need to memorize this. And so borate is BO3, 3-. So it's in group 3, here 3A or 13. And it has 3 oxygens with a 3- charge. And so we need to memorize this one. The other ones we can derive on the outer. The other ones are easy to derive based on the pattern. And so we don't need to memorize these. Like, for example, carbonate. Carbonate, how many oxygens? Well, it's the same number, CO3. What's the charge? It drops 1, so it's 2-, this carbonate. Then a nitrate, how many oxygens? 3 oxygens. This charge, it drops 1. And so we go, actually, we don't usually write 1-, we just write minus. And so that's just by convention here. That's a rule here. Let's do that. Here. So this is NO3- here. And so it goes 3, 2, 1, and we don't go below 1. And so there's no such thing as oxate. So this is a carbonate. This is nitrate. So we skip oxate. There's no and then we go to fluorine. Fluorine, which would be fluorate. Fluorate is going to follow the same pattern. It's 3 oxygens. and a minus charge. Minus is the lowest we can have for an anion. These are what we call anions. Anions have negative charge. Cations have positive charge. And so the smallest charge we can have for this is minus. But this pattern extends down here. Chlorine is next. This is fluorine. Chlorine is chlorate ClO3 minus. Bromine's next, which would be BrO3 minus. Iodine's next, which would be IO3 minus. And so this is what we call the outer. Now the inner is going to follow a different pattern. The inner would be anchored by silicon. And so you need to memorize silicon. Silicon is in group 4, 4A or 14. And so silicate, it's in group 4, so it's got 4 oxygens and a 4 minus charge. And so it's different than, yeah, carbon's in group 4 too, but carbon's in the outer pattern anchored by boron. Silicon's in the inner pattern and it's anchored by silicon. And so this is silicate. So we have to memorize, you have to memorize borate and you have to memorize silicate, but you look for little patterns here and there to help ease your memorization. And the rest we can derive. The rest are going to follow this pattern here. Let me do a different color here. Let's see if this is, and so when we look at nitrogen, we had nitrate. Actually, we did nitrogen. Nitrogen's in the outer. What's below nitrogen? What's below nitrogen is phosphorus. And so when we do phosphorus, we have phosphate. And so what is phosphate? Somebody tell me. Phosphate, well, it's going to follow this. It's going to be P, and then it's going to have 4 oxygens, PO4, and the charge, good, 3 minus. And so do you see, same number of oxygens, charge drops by 1. This is phosphate. Phosphate. Okay, then oxygen didn't work, but sulfur does. And then we have sulfate. Sulfate is going to have what? Somebody know, what do you think? Yeah, that's exactly right. Good, Francis. SO4, 2 minus, that's sulfate. Now, an interesting thing happens with this pattern. This pattern extends down. But the way it extends down is it's going to be the same. So for example, below silicon is germanium. And so germanate is going to be GeO4, 4 minus. That would be, below phosphorus is arsenic. And so arsenate is going to be the same. It's ASO4, 3 minus. And below sulfur is selenium. And so selenate is the same, SeO4, 2 minus. And then it goes on down. So below selenium is tellurium. Tellurate is, TeO4, 2 minus. And so the pattern extends downwards like that. And so arsenate's in common ones. Arsenate. Arsenate. Like that. Arsenate was in the news not so long ago because phosphate has this thing about links too. Have you heard of AMP, ADP, ATP? You heard of these? This is the fuel for cells, right? And so, yeah, energy. And so when we look at, let's take a look at ATP for a second. So we're going to link up, it's ADP, it stands for diphosphate, ATP triphosphate, AMP is monophosphate. So let's take a look at how those link up here. And so, we looked at dichromate here. Let's take a look at ADP, for example, ADP. Oh, ADP is payroll company, but ADP, See if we have some images for this. You know, phosphate is usually phosphorus with 4 oxygens, right? So let's take, this is ATP, sorry. But if we look at this phosphorus, it has 1, 2, 3, 4 oxygens. And this phosphorus should have 4 oxygens. But do you see, when we look at the link here, one of the oxygens is missing, just like in dichromate, one of the oxygens is missing here. And so when this links up, it likes to go POP rather than POOP. If it went POOP, then each phosphorus would have it. But this phosphorus is shared between the two here. And so the same kind of thing happens. Here's ADP down here with 2 phosphates that are linked up. But each phosphate should have 4 oxygens, but we have to double count this middle one because one of the oxygens is lost. Where did it go? Well, it went somewhere, and it went somewhere in the chemistry, you know. It just got rearranged. This provides a much more stable link. Well, arsenate's the same thing. It has the same structure. So actually, arsenate was in the news not so long ago because a NASA astrobiologist, well, this was actually kind of long ago, maybe 5 years ago or so, but a NASA astrobiologist, you know, they're looking for, astrobiologists are looking for extraterrestrial life. And this particular NASA astrobiologist was studying a lake in California. Actually, let me just show you what the lake looks like. Let me clear these drawings. That's a lake in California, just east of Yosemite National Park. It's Mono Lake. There are no fish in Mono Lake. This is Mono Lake. You know, there's actually life in here. There's a lot of bacteria, and there's brine shrimp here. The seagulls love to eat the brine shrimps. There's a lot of seagulls here, but this is pretty much a dead lake. It's not really dead. This NASA astrobiologist was checking out this supposedly dead lake. So they're collecting samples of the bacteria, and it turned out the bacteria had high levels of arsenic. And so what the biologist hypothesized was that this bacteria is a arsenate-based life form, not a phosphate-based life form. And so I shouldn't have closed that earlier page, but ATP. Where is that? This is it here. Let's look at this pathway here. The Wikipedia page. So rather than being a phosphate-based life form, this NASA astrobiologist hypothesized that this could be an arsenic-based life form, just based on how much arsenic is found in Mono Lake. And so rather than having a phosphorus there, they had an arsenic there. So it's exactly the same, pretty much the same thing. And so rather than making ADP, which would be diphosphate, it would be an ADA, diarsenate. And so rather than having phosphates linked, they'd have arsenates linked here. And rather than being an ATP here, it'd be an ATA, triarsenate. And so 3 arsenates linked up. That would be a, you know, because life on Earth is based on this, ADP and ATP. But, you know, maybe on different planets, you know, the phosphorus level is low and maybe there's high arsenic. And so maybe they're actually an arsenic-based life form out there. And so that was the hypothesis. And so that was exciting. That made, if you're familiar with scientific journals, that was published in Nature. Nature is one of the premier scientific journals out there, and it's very difficult to get published in there. Only the most significant scientific work gets published in Nature. And so let's see that article. It was Nature, that was arsenic-based life, arsenic-based life, Mono Lake. Yeah, that was published in Nature. So, well, this isn't the original article, and so the original article was here. When was this? Was what is it? Wikipedia mono-based. Oh, here it is. This is 2010. Sorry, it was like 10 years ago. The original article was published in Nature, but this is in Discover magazine. Monolake bacteria build their DNA using arsenic. And no, this isn't about aliens. So they're talking about this. This was the original study came out here. And they're thinking maybe, maybe this is interesting because it's pretty interesting. And this, I was really interested in this when it first came out. But of course, the scientists, if somebody hypothesizes this, then of course they're going to be skeptics and they're going to test this and people are going to try to repeat it. And so lots of scientific groups tried to repeat this and then test this. But actually, it's time for our break. Yeah. But what happened was nobody could repeat this. And so it was published and it underwent peer review, but this is how science works. Science is self-policing. And so immediately this started meeting up with challenges, and therefore lots of scientists started challenging this, here, let's look at this one here. Study challenges the existence of arsenic-based life. So other people are trying to look at Rosie Redfield says her findings are clear refutation that bacterium can incorporate arsenic. So this scientist published her findings saying that it's not possible. And then finally, that had to be retracted. 2 teams repeat much debated study and find that the chemical rules of life remain unbroken. That is, it's phosphorus after all. And so this is how science self-polices itself. And this is the beauty of the scientific method. The beauty of the scientific method is everything's going to be subject to everything's going to be subject to scrutiny, and then the good science will make it through, and then the bad science gets filtered out. There's a question about thiosulfate. Yeah, we are going to do thiosulfate, Kyle. There's a simple way of doing thiosulfate. I'll talk about that. That's not one you have to memorize. That one you can easily derive based on the word thio. I'll show you how to do that soon after our break. And then, and so these types of things are subject to scrutiny. And lately, a lot of things have been told by medical and scientific professionals, but they aren't really, they weren't, the way they were presented weren't subject to scrutiny. For example, when the whole idea of using masks came out, originally, there are a number of medical professionals that were saying that masks make absolutely no difference, and therefore do not buy masks. I remember that. Do not buy masks, all cap, exclamation mark, exclamation mark, exclamation mark, do not buy masks, do not buy masks. And I thought, what are the observations that you're basing that masks are totally ineffective at? And so I wanted to see observations. I want to see what that claim is based on. That's not going to meet scientific scrutiny. That's more of a political or a economic or some other statement. I'm not sure. And it turns out they were just trying to save masks for the people that really needed them, and the masks were effective. So there are a lot of things that the claims that people are making that you want to scrutinize, that you want, okay, what are your observations? What are the facts? What are the the laws that you saw that led to that hypothesis? So anyway, scientific method in action. We're going to come back. We're going to talk more about nomenclature after our break. So let's take a 15-minute break now, and then we'll come back and do more nomenclature. I'm going to pause the recording. Okay, we'll get started again. Just going back to this. Yeah, there were a lot of skeptics of this right when it was first published. And for chemists, the oxygen-arsenic bond is extremely weak. The phosphorus bond's a lot stronger. So that was one of the criticisms. Other criticisms came up, you know, the toxicity of arsenic and arsenates, etc. And it turns out that it was a mistake. You know, what the scientists thought was arsenic being incorporated there turned out to be contamination, essentially. So that's what it was sorted out. So it turned out to be the wrong hypothesis for that, wrong conclusion. All right, let's move on again to nomenclature. So for our nomenclature, we want to try to keep the memorization to a minimum, and then we want to use patterns to figure out as many things as possible. And so we'll look at some of the patterns here for some of these eights. We're going to do derivatives of some of these eights. And that is, for example, and this is good that this was brought up. One of them is like thio, like thio. Thio means sulfur. And so thio, for example, thiosulfate. So when you see sulfur like this, I mean, thio is sulfur, what you do is you replace oxygen with sulfur. They're in the same family, so it doesn't change charge or anything else. You know, sulfur is in the same family as oxygen, which is the chalcogens, you know. And so they're going to behave similarly in terms of many, many things. This is like arsenic and phosphorus are in the same family, but there are differences, you know, even though they're in the same family, they're going to be different properties, slight like bond strength, this kind of stuff. And so when we have the thio, so we take sulfate. Sulfate is in the inner block. It's 4 oxygens and it's a 2- charge. And so what we're going to do is we're going to take one of the oxygens and replace it with a sulfur. So rather than having 4 oxygens, what we're going to end up having is 3 oxygens. And then we have to add one more sulfur. Well, we already have a sulfur here, so we're going to change it to 2 here rather than 1. And so now we're going to have 3 oxygens and 2 sulfurs. The charge doesn't change. It stays the same like this. So this would be thiosulfate. And so whenever you see thio, we change oxygen with sulfur. There's some that I didn't cover. This is called cyanate. This is called thiocyanate. So the difference between cyanate and thiocyanate is we just replace the oxygen with the sulfur. Everything else stays the same. And so if you see that, that's a clue. In organic chemistry, we have alcohols. I used to work with alcohols a lot. Alcohols would be like this. This CH3CH2OH, this is ethanol. If I replace the oxygen with the sulfur, I make a thiol. This is called a thiol. This is called an alcohol. And the thiol just has a sulfur instead of the oxygen. And this is called ethane thiol here. You don't want to drink it though. Thiols are some of the worst smelling compounds known to humans. There's a lot of this stuff is like, I used to work with this type of stuff all the time, but a lot of this type of stuff is what skunk smells contains. It contains thiols. And one of my lab co-workers there at UCLA bought a brand new pair of tennis shoes and accidentally spilled a drop of thiol on their brand new tennis shoes. And he spent weeks trying to get rid of the smell, finally gave up and threw away the shoes. They were too stinky. And so even though, yeah, okay, oxygen and sulfur are in the same families, they're, you know, certain properties are going to be quite a bit different. Phosphorus and arsenic as well, same family. So, Okay, so we can derive things based on the ones we already know. So for example, the ites, I never memorize any of the ites because the ites follow a simple pattern. And so let's take a look at what that pattern is. Let me clear all these drawings here. And so when we have the ites, this is the simple pattern is one less oxygen than 8, same charge. And so we can go, let's look at some of the common ites. So nitrate, looking at the periodic table, is NO3 minus. Nitrite is NO2 minus. This would be nitrite. Sulfate is SO4 2 minus. Sulfite is SO3 2 minus. This would be sulfite. What other ones that are common? Oh yeah, chlorate. Chlorate is ClO3 minus. Chlorite is ClO2 minus. This would be chlorite. And so I don't bother memorizing the ites because the ites are easy to derive, you know. The same thing with hyper-8s. Hyper is, you know, too much, right? Too much. Hypo is too little. And so hyper-8s would be more than 8. Well, what's more than 8? And so if we do hyper-8s have one more oxygen than 8s. One more oxygen, same charge. Same charge. So what are some of the common hyper-8s? Well, if chlorate is this, then this would be, what am I saying? Hyper is too long. You know, hyper is a bit too long to say, and it's probably not the most, as far as connotation goes, the best. And so rather than saying hyper, this is what we're going to do. We're going to get rid of the HY part, and just call it per. Rather than hyper, we're going to shorten it to per. And when we do that, I don't know why we're at hyper, but I was thinking about something. So this is going to be hyperchlorate, or just for short, perchlorate. Perchlorate. So perchlorate has one more oxygen than chlorate, but same charge. Chlorite has one less oxygen than chlorate, same charge. And then we have hypo-ites. Hypo is too little, so one less oxygen than the ites. So this is going to be ClO minus. This would be hypo, it's too little. But we don't call it PO. We're going to call it by its full name, hypochlorite. Hypochlorite. So we have the hyper or per and the hypo. Those are the ones that are easy to derive. Okay, there are others that are easy to derive too from these. And the others are going to be acid anions, which I'm going to talk about now. And so let me write that over here. Acid anions. Acid anions are, we're going to take acid. Acid is just H+, and then add that to an anion. Plus the anion gives us an acid anion. And so let's look at some common acid anions. Common acid anion is if I take H+, which is acid, and we'll talk more about H+ later, and add that to carbonate, I'm going to form an acid anion. It's going to be HCO3. Now what happens with the charge is I got a positive charge here and a 2 minus charge here. So +1 minus 2 gives us -1. So this would be an acid anion here. This acid anion has a very simple name. It's called hydrogen carbonate, 2 words, hydrogen carbonate. So we just take a carbonate and add the hydrogen to that. We get hydrogen carbonate. Hydrogen carbonate is also known as bicarbonate. Bicarbonate is often used bi versus di. You know, di usually refers to 2. Bi usually refers to 2, but in this context, it refers to an acid anion. So bicarbonate is hydrogen carbonate, which is HCO3 minus. It's an acid anion. Now, if we add another H plus, we get an acid. Acids are neutral. This is an anion. Anions have a negative charge. But let's say if I take H plus and then add that to HCO3 minus, then I get H2CO3. H2CO3 is an acid. Acids have no charge, you know, because now the charges are balanced. +1, -1 is H2CO3. It's neutral. All acids should be neutral. Acid anions are going to have a negative charge. Neutral. This is called carbonic acid. And so acids, if I look at this one's, well, I'll talk more about it and the names of the acids later. But, we'll look at them. And so this is not an acid anion. We're looking at acid anions right now. So what are some other common acid anions? Well, if I take an H plus a sulfate, I'll get HSO4 minus. HSO4 minus. HSO4 minus is just called hydrogen sulfate. Or you know, here's that word again, bisulfate, or the prefix, or bisulfate. H plus and sulfite, SO3, 2 minus, makes bisulfite, HSO3 minus with bisulfite, or hydrogen sulfite. Phosphate's an interesting one because if I take H plus and phosphate, PO4, 3 minus, I can make HPO4, 2 minus. But if I take H plus and add that to HPO4, 2 minus, I can make H2PO4 minus. If I take another H plus, I'm going to get neutral. I'm going to get acid. So these are 2 acid anions. Now I can't call these both the same things. I can't call this one biphosphate and this one biphosphate because they're different. And so this one, we can't use the prefix bi. We have to use this. Now we can't call this hydrogen phosphate and this one hydrogen phosphate because they're different. And so this one we call monohydrogen. Monohydrogen is one word and the phosphate's the second word. So this is monohydrogen phosphate. Acids are always neutral, Kazra. Acids are always neutral. Acid anions are going to have a negative charge. So we're just looking at acid anions right now, and then we'll look at acids next. This one's called dihydrogen phosphate. Dihydrogen is one word, phosphate's the second word. Dihydrogen phosphate here. Again, with a B, it implies something different. Not 2, but acid. So these are acid anions. The acid anions are easy to derive, you know, so we're trying to keep memorization to a minimum and be able to derive as many things as possible rather than memorizing them. Acid names we don't memorize. Now, your Chem 4 book is going to ask you to memorize acid names. I never memorize acid names. And so I don't know why I didn't make I was supposed to make a PowerPoint slide for acids. Now we're going to talk about naming acids. Okay, so we're actually, should we name acids? Yeah, and then ionic compounds. Okay, we learned to name the ions, and then I'll just do a quick aside in acids right now. The acids name it's going to be a cation. The cation is always the same. The cation's H plus. and the anion. The anion's different, depends on, you know, what acid we're on. And so some anion, and this is going to make the acid. And it should be enough cations to neutralize the anion. And so, for example, if the anion is minus, then we're going to form HX. If the anion is 2 minus, then we're going to form H2X. And if the anion is 3 minus, then we're going to form H3X, because, you know, we have to neutralize those 3 negative charges with a positive charge on the H plus here. And so this acid is called the monoprotic acid. This is diprotic. This is triprotic, you know, because H plus we call a proton. You know, this is called a proton or the hydrogen ion. The reason they call it a proton is because most hydrogen atoms only consist of a proton and an electron. So if we lose the electron, we're just left with a proton. So this is a proton. If we're dealing with H1. If we're dealing with H2, hydrogen 2, then we are left with a proton and a neutron. But, you know, 99.9% of the hydrogen is H1. And so for 99.9% of it, we're just left with a proton if we lose the electron. What should we memorize? You have to memorize the things I said to memorize. That is the 8s that aren't on the pattern, like chromate, dichromate, those, right? But if you don't know how to do the pattern, then you're going to have to memorize all these. Everything we talked about, you have to have memorized or be able to derive. Being able to derive means you don't have to memorize as much. But for some reason, people have a hard time learning the pattern. And for those that have a difficult time learning the pattern, I suggest memorizing everything. Maybe some people find it easier to memorize than learning some pattern. Because the pattern is not in the book, you know, so be aware of that. The pattern's not in the book. If it's not in the book, a lot of people don't think they want to memorize it. Well, let's take a look at the acid name. The acid name is based on the name of the anion. The cation's always the same, it's H plus, and so the only difference is the anion. And so we only have 3 types of anions. We have the anions that end in IDE. And so if the anion ends in IDE, then the acid, we do this. We change, or we add the hydro prefix. We change the name of the anion a little bit, maybe, to clean it up, and then we add the ic acid suffix. And so it's hydroic. Hydroic acids are always anions that end in IDE. The anions that end in ATE, 8, are going to have just the ic acid. And so we change the ending here. The anions that end in ite, we use the Aus acid. And that's it. And so figuring out the acid name is, all we need to know is, we need to know, does the anion end in ide, ate, or ite? And so let's look at some acids really quick here. Delete that. All right, I'm going to look at a series of acids here, and then we'll just consider this series of acids initially. Starting off with HClO4, HClO3, HClO2, HClO. All right, so we look at the anions here. Well, the cations are all the same. So when I look at the anions here, I see ClO4 minus. This one has the anion ClO3 minus. This one has the anion ClO2 minus, and this one has the anion ClO minus. Okay, which one of these is chlorate? Usually when we have a T, it usually is oxy. Usually, this is a rule, this is not a law, but these are called oxyanides. Usually, not always. When we have a D, D that usually is monatomic, but not always. Monatomic means single ion, single atom. And so which one of these is chlorate? Well, you know, look at the periodic table and yeah, this one's chlorate. If this one's chlorate, then this must mean it's chloric acid. Because what we do is we take the anion name chlorate and then just change it to ic acid. 8 goes to ic acid, so this is going to be chloric acid. This is, what's this one? ClO4 minus called. Has one more oxygen, so it's hyper, but we don't use hyper. It would be perchlorate. So if this one's perchlorate, then, well, it's an 8, so we just change it to ic acid. So this is called perchloric acid. So this is the 8s here. Now this one is chlorite. You know, chlorite has one less oxygen than 8. And so that's an ite. So that's different. That's an Aus acid. So chlorite, we change the ending. We call it chlorous acid. And this one is, this is hyper. This is going to be hypo. So this is hypochlorite. Hypochlorite, well, it's ite, so we're just going to call it hypochlorous acid. Hypochlorous acid. And so that's how we do it. So we'll take a look at some other common ones, like this one's very common, HNO3. HNO3 this is nitrate, so we call it nitric acid. That's a very common acid. HCl is another very common acid. This is chloride. Chloride, it's an ide. So chloride gets hydro, and then chlor, and then we're going to change the ending from ide to ic. And so it's going to be hydrochloric acid. And then what's another common one? Common one would be this one, H2SO4. You know, sulfate's a 2-, so it needs 2 hydrogens. And so this is sulfate. Sulfate, we should call it sulfic acid. But sulfic acid doesn't sound appropriate. And so this one, we add a syllable here. Rather than going from sulfate to sulfic, we're going to go from sulfate to sulfuric. And so this is sulfuric. Sometimes we do that. The same thing happens with phosphate. Phosphate should go to phosphic acid, but it doesn't sound right. And so this one goes to phosphoric acid. So a syllable was added there. You're right. Acetic acid is very common. Acetic acid is HC2H3O2. That's acetate. So acetate goes to acetic. And so this would be acetic acid. Acetic acid. One of the ides I asked you to memorize, this is an ide that you don't get off the periodic table, but it's cyanide. And so this is cyanide. Cyanide, it's an ide. And so this one's going to be called hydrocyanic acid. Hydrocyanic acid is based on cyanide with a D here rather than a T. So hydrochloric acids. HF is hydrofluoric acid, fluoride. HBr is hydrobromic acid. HI is hydroiodic acid. So those are the acids. Okay, these are acids, and then we have other compounds that are made up of ions, which you call salts, or just ionic compounds, you know, in general. And so let's look at naming ionic compounds next. I'm supposed to make more slides, so I'm going to clear this one, then we'll continue. Why wouldn't it be hydronitric acid? It's only, hydro is only when the anion ends in D, I-D-E. This one is nitrate, and so it ends in A-T-E, so it goes to nitric acid. That's why. And so we have to have an ide. So we think of all the ides that we had. Actually, we can do that here. Let's do a little summarizing chart here. Clear my drawings here. Let's take a look at the periodic table and look at the ions that we have. And so I'll try to do this best I can. H is that H when it, you know, species over here on the left tend to lose electrons, H plus, and then we have Li plus. And then go on here, lithium, sodium, potassium, rubidium, cesium. So we should know all these. Okay, so this is the hydrogen ion or the proton. This is lithium ion, sodium ion, potassium ion, rubidium ion. These are all fixed charged, and they're fixed charged at +1. And so we should be able to name all these. Okay, then we have beryllium, 2+, and then magnesium, 2+, and calcium, 2+, strontium, barium, +. These are also fixed charge. So this is a beryllium ion. Beryllium ion is not that common because beryllium is very toxic. We need magnesium and calcium for good health. But sometimes what happens is beryllium gets in there and interferes with it. Fortunately, beryllium is not that common. It's pretty rare. But beryllium is not good for life. Magnesium and calcium are essential. Strontium, there's a lot of radioactive species in strontium. Radioactive isotopes of strontium, I should say. Those are fixed charge. And so the name of these fixed charge ones is just the name of the element plus the word ion, magnesium. So if we jump from beryllium all the way, we can jump over here to aluminum. You know, aluminum is 3+. If we go from magnesium, let's see, where do we go? We should probably look at the periodic table for this. So I'm doing this memory. But if we go from magnesium, let's see, sodium, magnesium, we got scandium. It should go. No, actually, 1, 2, 3, 4. Not scandium. Scandium's down here. You follow along with the table here. Scandium should be here. Scandium, actually aluminum's one down here. I didn't line it up quite right. Beryllium, it doesn't go to aluminum there. Let me just write it down here. These are common fixed charged ions. Aluminum should be lined up here in the third row. This is called the period. And the beryllium, it goes from lithium, beryllium, comes after beryllium. Boron. Boron's here. The aluminum's below it. Boron, we don't see that much as an ion, so we don't really do much with boron. But boron would be a 3+, you know, if it were an ion. You'd expect to be a 3+. And then let's continue on here. Potassium, calcium, scandium was 3+. And then after scandium comes titanium. Titanium, okay, this is fixed. It's fixed. Now titanium is what we call variable charge, you know. So we're starting to get into the variable charge species here. Titanium. What does the charge range from? Well, very common charge for titanium is 4+, you know. But the charge for titanium runs from +1 to 4+. This is what we call the oxidation state. +4 ions are very rare. +4. Probably the highest ion that we see usually is a +3. And so once we get to 4+, it has to be stabilized by something. You know. So we see free ions. I'll talk about what free ions mean. Free ions mean they don't have to be stabilized by something else. But you know, so we see up to about +3. So free ions are going to go up to about ± 3 max. Higher charges require some type of stabilization. Require some form of stabilization, some form of external stabilization or internal, well, internal, external is kind of confusing, stabilization. So in order to get titanium in the 4+, it's got to be stabilized by oxygen. And we'll see that later. So we got that. Titanium and the vanadium. You know, vanadium ranges from +1 to +5. Now +2 and +3 are commonly stabilized. So, you know, +2, +3 are the most common charges, vanadium. And then chromium, etc. And so let's take a look at the periodic table and then see some of these charges here. Get a simple one here. You can just draw right over this one. It'll be okay. Just add. Oh, don't do this to me. Use this one. This is in Russian. That's okay. So what do we want to know the names for? Well, we want to know the names for things like hydroxynitric acid, hydrohydroxic acid, hydroxide, yeah. Okay, hydrohydroxic acid, yeah, that's possible. Let's look at that for a moment here. I missed these questions here. Hydrohydroxic acid, hydroxynitric acid. Hydroic must mean we're dealing with hydroxide. And so hydroxide is one of those ones you just have to memorize, OH minus. And so to make the acid, we take an H plus, as many as required, and in this case, it would require 1, so it would form H2O, 2 hydrogens, 1 oxygen. And so hydrohydroxic acid is AKA water. That's one way of talking about water. Now, acids are borderline. You know, acids are also binary. These are called binary molecular compounds. Binary molecular compounds. And well, molecular means it's made of nonmetals, right? But acids, you could use either naming system. You could name it as an ionic or a non-metal molecular type compound, or an acid. And so you can come up with 3 names for water. You know, depends on how you want to name it. We haven't talked about naming ionic compounds, but another name for water would be hydrogen hydroxide. Hydrogen hydroxide is the hydrogen cation with a hydroxide anion. It's like sodium chloride. You know, we name the cation, which would be Na+, and the anion Cl-. Well, this would be hydrogen hydroxide, another name. Or hydroxyic acid, or there's one more name for water. And the other name for water is naming it as a binary molecular compound. It would be called dihydrogen monoxide. And so if we name this as binary, 2 elements, molecular, it's all nonmetals, and we can come up with dihydrogen monoxide. That's another name, AKA water. And so water is its common name, and then chemically it could be called dihydrogen monoxide, hydrogen hydroxide, or hydroxyic acid. Okay. If somebody told you you're drinking hydroxyic acid, you might be scared because what the heck are you drinking? Or if somebody told you you're drinking dihydrogen monoxide, have a glass of dihydrogen monoxide, you might be scared as well, because you probably wouldn't want to drink dihydrogen monoxide. But you shouldn't be. You got to make sure. You got to make sure they're not making a mistake. For one thing, you know, if you're offered a monoxide. And so, have you seen this? DHMO.org, you know, dihydrogen monoxide. Dihydrogen monoxide, DHMO, is a colorless, odorless chemical compound, also referred to by some as dihydrogen oxide, hydrogen hydroxide, hydronium hydroxide. Hydronium hydroxide is okay, but not really. Or simply hydric acid. Hydric acid, well, that's shortening this a bit too much. You know, I can understand. I'd rather call it hydroxyic acid. But it sounds scary when you read about it, you know. And so they're trying to get cities to ban dihydrogen monoxide, or DHMO, and some cities actually enacted a ban about this. You know, all these are true. It's toxic. You know, in large quantities, DHMO is toxic. You know, obviously you could drown. You know, and so this is just. So a page like this, well, I don't know if you want to support the effort to ban DHMO, but some cities came close, including cities in California. City ban of DHMO. Yeah, it's a hoax, obviously. That was a hoax. City officials fall for internet hoax. In large quantities, dihydrogen monoxide can cause medical problems in humans, can destroy properties. In Liso Viejo, they fell for it. And they wanted to ban DHMO. Obviously, banning DHMO would be fatal. So they fell for the hoax until somebody told them it was a hoax. See. Okay, I thought they were asking for donations, but DHMO kills, and ban DHMO. Does an acid have to have a pH below 7? An acid, yes. An acid solution does have to have a pH below 7. However, when we look at acids in a more general context, there are some things that are potentially acidic that we ignore the pH on, you know. So there are molecules that are both an acid and a base. And like, for example, let me give you an example here really quick. Amino acids. This is probably not the best example, but when we look at a typical amino acid has two parts to it. There's the amine part, which is what we call a base, and then there's the acid part over here. And so there are a lot of compounds that have both an acid and a base site. Here's an acid site and here's a base site. So they can go either way, you know, they can act as an acid or they can act as a base. And so even sometimes one dominates over the other. Sometimes it's a much better base than it is an acid. And we have those kinds of circumstances. If it's a much better base than it is an acid, it could potentially have a pH that's greater than 7, but still have the possibility to react as an acid. We're going to see this structurally when we get into structure a lot more. And so this is why we want to understand structure a lot more. So amino acids have different forms. They have the acid form of the amino acid, they have the base form. And so let's look at the, even though we call an acid, you know, amino acids as bases, amino acids as acids, and it's because it can go either way. This is called the, this would be the base form of the amino acid here, you know. And so then we have the zwitterionic form, the amino acids. So a lot of molecules are like that, you know. When we look at it structurally, we can see an acid site and a base site in the same molecule. In fact, I just did one in Chem 1B, which was called, what was it called? Imidazole. Imidazole's pretty interesting. Imidazole, I misspelled it. But imidazole is one of these ones where it has acid and a base, and it turns out the base is much stronger than the acid. So the pH is actually greater than 7, but it can act as an acid because there's an acid part of it here. But that's getting into more advanced topics. So let's go back to the periodic table and then let's try to figure out, we're going to write out all the ions and stuff here. Let's get a decent, I want a big periodic table. Should have just taken the one from the book. Except I was looking for the one from the book the other day and it just didn't come out right. Okay, that's not coming. Yesterday I was looking for the one from the book. Let's see, I looked at the back of the book. There's a nice periodic table because it doesn't show much in our book. But it doesn't, and the ebook doesn't have the inside cover or the back, you know, the book. I was looking for the periodic table from our book. And so let me see if I can just get that. Maybe it's in chapter. I didn't search. Oops, misspelled table. And that's what I got last time. I looked at this and this was what I got. This is not helpful. I can't believe they don't have one. P table. All right, let me try that. Thank you. Appreciate it. Well, I want one that's blank below here. But it's all right. We'll just do this like this. I guess what we'll do is this. Okay, I'm going to put another sheet in here. We're going to do some drawings in here. Actually, maybe I'll just draw on top of this here. All right. Can I draw on top of this? Let me see. Yeah, I can. Okay, again, these are fixed charge. These are cations. And the cations are going to lose. Let's say lithium has 3 electrons. It wants to lose 1 to be like helium, 2 electrons. Hydrogen loses 1 to end up at 0. Put 0 there, but it turns out that's favorable. All these, the only thing that changes is that we have to add the word ion. So it's not the neutral element. This is ion. This is plus, plus. This is what I was drawing out earlier. Francium is radioactive. So francium we don't see much of, so we'll just leave that out. So you don't have to worry about francium. Beryllium's not that common, but it's so toxic, you should know about it. It used to be, beryllium, like magnesium, used to be used in aircraft industry. Beryllium is a very lightweight metal, and structurally it's pretty strong. So beryllium was used. However, all the machinists that were machining beryllium ended up dying from beryllium poisoning, unfortunately. So they stopped using it. Calcium, strontium, these are all 2+. Barium, radium is radioactive. So radium, though, radium is, Curie. So there's some historical significance of radium. So let me leave that in there. Scandium is important. Yttrium, not so much, but yttrium is always 3+. Scandium we'll throw in. These are always, so scandium, this would be called the scandium ion. However, for titanium, titanium varies from, +1 to +4, depending on how many electrons it uses. So we have to add a Roman numeral. So if it's titanium +1, we would add titanium Roman numeral 1, Vanadium varies from +1 to +5. Chromium is going to do the same, +1 to +6. How do I know +6? Well, 24 minus 6 is what? Well, 24 minus 6 is 18. Well, what has 18 electrons? Argon. Manganese is 25 electrons. So if we do 25 minus 7, it gives us 18. So if we lose 7, it goes to +7. So +1 to about +7. Iron, +1 to +8. And it kind of maxes out there. We don't really go much higher. And then we drop back down, This is called group 2B. 1B. This is group 1B. This is group 2B. Copper is plus. Zinc is 2+. It's always fixed charge. Zinc, cadmium, and silver. These are fixed charges here. Cadmium's 2+, silver's plus. Copper is unusual because it's +1 or +2. It's common. And so this is what we call, the kind of the charge range here. So we're going to leave that like that. But the most common charge of these, let me just write over this. I'm totally right over this. So the most common charge of these is +2. Actually, that's not so visible. Try to do it again. Color. Do white. +2 and +3. I'll talk about this a little bit later, but this is the most common charge observed for these. And so, for example, iron with a +2 would be called iron 2, and iron with +3 would be called iron 3, and we'd write that with Roman numerals. So iron 2 is very common, like iron Roman numeral 2, iron Roman numeral 3. So we already talked about this. We called this one ferrous, this one ferric here. So we got. This is +2, +3 in this region. Those are common charges for this region. Common charges for this region here are +1 and +2, +1, +2, and +3 for gold. Gold is +1 and +3 are the most common. Mercury is +1, +2. So these are common charges in this kind of area. And so let's write +3 for gold. Gold is unusual though, but +1 and +2. And then over here in this area, +2 and +4. You know, again, we're in variable charge. +2 and +4 are common here. So we had tin2, which is SN2+, and tin4, which is SN4+. And same thing with lead, 2,4. Actually, it's really only this. Over here, it's more like 3, 5, you know, in this area. I should write 2,4 here. 2,4. This is more 3, 5. So let me erase some of that. This is like +2, +4. This is +3, +5 in this area here, usually. Now, boron and aluminum, you know, +3 is good charge for these. You know. +3, 3+, 3+. We usually write the number and then the charge after that. Now, carbon's right in the middle. Carbon can lose 4 if it has 6 electrons. So if it loses 4, it ends up at 2, or it can gain 4 to be like neon. So carbon varies from +4 to -4. Nitrogen can lose 5 to be like helium, or gain 3 to be like neon. So this is going to be, if it loses 5, it'll be like +5 to -3. Oxygen can lose 6, +6 to -2. Fluorine can go +7, although fluorine doesn't really go +7. I'm just saying in this column to -1, -1. And so what are the common charges of these? Well, if you look at the common charge, like for example, if carbon gains 4, then we form carbide. And so this is what I want to draw out. And so we're going to draw out all the variations of these guys over here on this part of the periodic table. And so that's what I'll do next. If I can blow this up. Clear all these drawings. And so what are some of the common ions that we're going to see over here? And, let's just focus on this. So when we have an anion, we change the ending. So this anion would be 4-. It wants 4 extra electrons. So each electron is an extra negative charge. So this has 4 extra negative charges. And that means 6 electrons plus 4 electrons is going to give us 10 electrons, like that. That's the pattern we see. This is called carbide. Carbide. It's a monatomic anion. And so that's why the IDE ending comes in there. And then we have CO3, 2-. This would be carbonate. Carbonate. So these are 2 very common carbon-based anions that we see here. And then when we look at carbonate, It's kind of interesting. If we look at carbonate, this is what I mean, like 4 minus has to be stabilized. So for example, how's that stabilized? That's stabilized in something like silicon carbide. Silicon carbide is silicon's in the 4 plus, you know, silicon. In this case, silicon's in the 4 plus, and then carbon is in the 4 minus. So silicon's 4 plus, it's 14. So if it loses 4 electrons, it'd be like neon, 10. And so that's losing 4. If it loses 4 negative charges, those protons aren't going to be balanced. You know, I'm going to have 14 protons with only 10 electrons. 14 protons with 10 electrons is going to have an excess of positive charge. So silicon carbide is this. So silicon cation with a carbon anion like that. Now carbonate's kind of interesting. You know, carbonate, if we consider oxygen, what's the charge on the oxygen likes? Oxygen likes to form O with a 2 minus charge. You know, this is what we call oxide. And so if oxygen has 3 oxygens, actually, no, 4, 3. Each oxygen's minus 2. And then I have 1 carbon plus 3 oxygens gives us a net charge of 2 minus. That means one of these aren't going to be eliminated. So this is 4 plus. If I take carbon in the 4 plus, so it's plus 4 minus 2 gives us 0. Minus 2 gives me a minus 2. And so carbonate has a carbon in the plus 4, but it's stabilized by these oxygens. So this is what I mean by stabilized by the oxygen here. The carbon would be a plus 4 in this case, although technically it's not exactly. Do we need to know all of these charges? Yeah, the patterns in the charges you need to know, and these charges you definitely need to know. For example, nitrogen is 7 electrons plus 3 gives us 10. So 3 extra electrons gives us 3 minus. So N3 minus is called nitride. Nitride. And some common nitrogen oxyanions would be nitrate. This is nitrate. And nitrite, NO2 minus. This is nitrite. Common. Oxide is like this, but we have other oxygen containing anions. It doesn't have to be 2 minus like this. It's 8. 8 plus 2 gives us 10. But we could have things like this, O2 2 minus. If I have 2 oxygens, each one has 1 electron, gives us 9. O2 2 minus isn't as stable. It's reactive because if we only have 9 electrons on each oxygen, then it wants 1 more. And so this is called peroxide. Peroxide is not stable. It's reactive because it wants 1 more electron for each oxygen, you know. So each oxygen can have 10. And then we have O2 minus. O2 minus is called superoxide. Superoxide is not stable either because 1 oxygen's at 8 and the other is at 9. So we're not quite at 10 for both. And so these are some of those. Then we have F minus. F minus is pretty much the only one we see for fluorine, and this is fluoride. However, chlorine, we see more. We have chloride, like that. And then we see these ones, ClO minus, ClO2 minus, ClO3 minus, ClO4 minus. Now over here, we expect it to range from plus, we go to 2 here, so we're at 9. So it's gonna range from plus 7 to minus 1. That would be the range. Plus 7 would be losing 7 out of the 9, which would give us 2. Plus 7 here would be losing 7 out of the 17. If we lost 7 out of the 17, that gives us 10, like that. So let's look at chlorine here. When we look at chlorine here, these are little patterns that we see here. And so some of these charges have to be stabilized by oxygen. And so, well, chlorine can exist as the free ion. It doesn't have to be stabilized by oxygen, and that's minus 1. If we look at ClO minus, what we have to do is we have to envision this as being a oxygen. Oxygen likes minus 2, otherwise it's pretty unstable, you know. And so if oxygen is -2, what does that mean chlorine has to be? Plus X. So we have plus X minus 2 gives us a net charge of -1. And so what is X here? Well, X has got to be +1. And so this means that in this one, I put this in parentheses here, chlorine is +1 in ClO minus, because oxygen's -2, -2 plus 1 gives us minus. Let's go to ClO2. If I go to ClO2 minus, each oxygen's -2, and I have 2 of those. So -2, -2. So that's -4. -4 plus what gives us -1? So that means chlorine must be a -4 plus 3. So this has got to be +3, that chlorine. Let's go to ClO3 minus. If I look at ClO3 minus, I have 3 oxygens. Okay, was there a question? Okay, I got it, Crystal. Thanks. This is being recorded, so we're okay. I don't know what we're doing with time. Let's see. 1:05 is our last break. So our next break will be at 2:05. All right, so we have 3 oxygens here. So each oxygen is -2. Let's say like oxide is -2, that's stable. So it's -6. -6 plus 5 will give us -1. So chlorine here is +5. And then let's look at ClO4 minus. If we have 4 oxygens and each oxygen is -2, so -2, -2, -2 gives us -8. So 4 oxygens of -2 is -8. -8 plus 7. -8 plus 7 gives us -1. Now, the question comes up, what about hyperchlorate? Can we have a hyperchlorate or perchlorate? Would a perchlorate exist? And we would predict a perchlorate would not exist. Let me try to make a perchlorate. And so if I take perchlorate, which is ClO4, and then add another oxygen to call it ClO5 minus, maybe we could call this hyperchlorate, so perchlorate. The question comes up, would you expect perchlorate to exist? The situation here is I have 5 oxygens, so 1, 2, 3, 4, 5 oxygens. And let's give oxygen its favored charge. Oxygen's favored charge is 2 minus, so that's -10. So I have a cumulative charge of -10 from the oxygens. That means chlorine must be +9. Because +9 minus 10 will give us the net charge. This is called the net charge of -1. But if it's +9, well, if chlorine lost 9 electrons, so it has 17 electrons, if it loses 9 of those, it's going to pass this, and we're going to go to 8. So chlorine's going to be 8 electrons. Well, 8 electrons is not so stable. Oxygen is 8 electrons, and it doesn't want 8 electrons. Oxygen wants 10 electrons. And so this one, a perchlorate, we don't predict to exist because this is exceeding that. You know, it's either going to gain or lose electrons to be nearest noble gas. So chlorine can lose 7 to be like 10, or it can gain 1 to be like 18 argon. And so what we're going to see is the charge on chlorine is going to vary from -1, so it's like argon, to +10. So it's like neon, but losing 7 electrons isn't so easy for chlorine. So this is why we see +1, +2, etc. We see different charges to make it a little easier, because sometimes it's not as easy to lose that many electrons. If you don't quite get this right now, don't worry about it. But yeah, we're just talking about the formulas, but there's certain things that can clue you in, you know. For example, perchlorate, was that ClO5 or was it ClO6 or was it ClO4? You know, per is the max. So, you know, the max we're going to have has got to be 4, because it's 4 of these, 4 minus 2 is -8, and that gives chlorine at +7, which is going to be the max positive charge, because if we go more, we're going to get to 9, 8, 7. That's less stable. I'm going to stop at 10. So these are little tricks you can use to help you remember these formulas. But anyway, let's take another break here. I'm gonna stop the recording here and then make another recording here. So we'll take a 15-minute break.